7com Consulting. Deliver innovative services and products to maintain the UK's roads and pavements. Building on the talent and experience of our highly motivated people, we enhance the life of assets through value engineering and value for money services, incorporating consultancy, design, maintenance and redevelopment. The Edgbaston campus of University of Birmingham is green and spacious, with all the amenities of a small town on its 101 hectare, including the university very own train station, allow the campus to be very accessible from various transportation. After the recent completion of the new development of the library, the campus is planned to begin the Project Green Heart, with work soon begin in early 2017. It is expected that greater number of construction vehicles will be accessing the construction's site, located in heart of campus, plus other ongoing working sites located across campus. Road network in Edgbaston campus provide a vital role for staffs, students, visitors, and construction workers to access the campus through cars, cycles, or even larger vehicles such like coaches, construction vehicles. However, even with adequate maintenance, pavement will deteriorate over time. The rate of deterioration will depend on a number of factors, including the traffic loading, pavement design strengths, the climate and environment. Eventually there are needs for pavement maintenance, upgrading or reconstructions. So why is road management important? The major aim of road management is to maintain and improve the existing road network, to enable its continued use by traffic in an efficient and safe manner. Road asset management has the purpose of maintaining and improving the existing road network, to enable its continued use by traffic in an efficient and safe manner. Appropriate management must also take into account issues of effectiveness and concern of the environment. Road management can be seen as a process that is attempting to optimize the overall performance of the road network over time. Maintenance reduces rate of pavement deterioration. It lowers the cost of operating vehicles on road by improving the running surfaces, keeping the road open on a continuous basis. Maintain the level of services, road conditions and to improve safety, decrease the overall road agency cost for accident clearance. Considering the road management process as a whole, a management cycle can be identified. The cycle provides a series of well-defined steps that take the management process through the decision-making activities. Decisions made in each step of the cycle used an up-to-date information which should sit at the heart of the management cycle. The information is shared and used in each of the stages for the best of decision-making. The key step in assessing needs is the collection of data. These data provide information on the extent of the gap between the present level of service or standard that's set out in the aim being sought. When the data is grouped and refined after the ANA, there will be choices to be made about the activities required to meet the aims. Actions identified must be costed and rationalized to set priorities for which the best value schemes are adopted. A review process must form an integral part of needs-based road management. This process should include monitoring and auditing to perform feedbacks and checks to the management process, so that when next cycle of management takes place, the management team obtain valuable information and learn from past experience to refine problems, failure into considerations, develop a better schemes. The aims of this project is to develop a pavement management system to assess the maintenance needs of university's Edgbaston campus road network, and to maintain the level of services, road conditions and to improve safety for road users. Project objectives of this project is to assess the current road deterioration conditions in campus, by desk study and field surveying. Design a management regime to recognize which parts of the pavement are in bad conditions. Our team will need to establish a decision support system to prioritize treatment actions by condition-based systems. At last, provide any immediate or long-term solutions with respect to the decision support system. The main constraints of this project are the lack of provided information and measuring equipment from our client. Our team was provided with basic measuring equipment such as the measuring wheels and Merlin, which these manual equipments are both used for field surveying. Thus, no existing or previous data were supplied by the client for further analysis. Hence, our team decided to adopt the Information Quality Levels, IQL, as IQL4. L4 provides basic summary statistic of inventory, performance, and utilization of interest to provider and users. It is suitable for the simplest planning and programming model for very low volume roads. Basic data collection methods. The project is classed as in a programming stage. Refer to the process of management. This stage includes basic course data and a cost analysis was undertaken to determine the economic feasibilities of each set of the work. Following assumptions were adopted throughout the entire project. Traffic condition in the campus is assumed as less than 3 MSA for calculating priority index. All drainage conditions in the condition-based system assume they are in excellent conditions. Field data presented in this project only reflect pavement condition on the sampling dates, 24th-26th of March, 2017. Another constraint is that, notice not the whole management is considered in this project due to the lack of information provided. Activities implementation, monitoring, auditing are not included in this project. Information groups in data collection can be identified as inventory and pavement condition in this project. The inventory include network referencing, which break the road network into successively smaller sections and subsections, with a unique reference for each of it. Item inventory relate to features of the road network. It record items such as length, width of the roads or details like road signs.
Computer software Google Earth is used as a tool in the planning stage when performing desk study. It is used to examine the overall topography area to give groups an estimate and overview of the local topography area.
While it can also be used to estimate measurements, such as the length, width of road sections. The software assists our team to plan the network and item referencing system through satellite aerial photography before field survey, enhancing our field survey efficiency during field surveying. The field surveying includes using Merlin to measure the road roughness, giving visual inspection to any surface distress and structural defects, while compare measurement estimated from Google Earth to confirm the final inventory data. 5 main road networks were included in the data sampling, as there are one of the busiest road in the campus. There are Terrace Road on the south side of campus, near the Civil and Mechanical Engineering building. SW Campus Road and University Road West are on the west side, near the Building of Bioscience. The Ring Road South and Ring Road North connect north and south side of the campus separately on the west and east side respectively. This part of the video illustrates the inventory list that was used for data storage and organization in our project. Pavement condition is assessed by visual inspection and measuring defects, and it is convenient to group these in terms the following parameters: roughness, surface distress and structural capacity. Roughness is measured as a longitudinal unevenness of the road and is the major determinant of changes in vehicle operating cost, which is therefore probably of most greatest concern to road user. Roughness is measured by equipment called Merlin in this project. The unit adopted is International Roughness Index, IRI. Surface distress concern about uneven patching, rutting and polished aggregate in this project, while they are assessed by visual assessment. The structural capacity is assessed by visual assessment. It concern the ability of the road to sustain traffic and environmental loading. Untreated cracks and potholes can lead to water ingress of road base, resulting ultimately in structural defects. The Merlin was developed by the Transport Research Laboratory for use in developing counties. Merlin is easy to use, self-calibrating, robust and can be constructed with readily available components. Merlin measure the roughness of a road section by measuring the vertical distance between the road surface under the probe and the center point of an imaginary line joining the bottom of the 2 feet. Measuring wheel is equipment that is lightweight, compact and economic to use. It is used for measuring the overall lengths and cross-section of subsections road networks. The following video will demonstrate the use of Merlin and measuring wheel for data collection.
Defined in engineering practice as surface unevenness which adversely affects ride comfort. Expressed by a numerical scale named International Roughness Index, IRI. After data collection stages, data are input into Excel for organization and filtering. Pavement condition data are identified as structural and functional defects and IRI. The number of cracks, potholes, rutting, uneven patching and polished aggregate were observed in visual inspections, and converted into percentages, in a ratio to the total area of each of the road sections identified in the network referencing system. After the data analysis, a first-generation decision support system takes place. It uses intervention levels to determine types of treatment sections, the number of treatment options considered per section. Prioritization method based on treatment-based methods is used to give priority to pavement maintenance sequence. In terms of treatment actions applied to the pavement, there are at least 2 options of actions are considered. They are do minimum and do something options. The do minimum options include actions of doing nothing and routine maintenance, while the do something options include immediate maintenance and reconstruction. In total, 4 generic action of treatments are established for pavement maintenance. The first generation decision support systems is based on defectiveness index, where priority index is determined on the choice of treatments to be applied.
priority index can be expressed as the formula shown. The calculation of priority index required a set of intervention levels to establish minimum thresholds for treatment's hierarchy, and they are identified in the following tables. The treatment hierarchies are identified as 4 major roles. 4 treatment options are do nothing, routine maintenance, immediate maintenance, and reconstruction. These treatment options are pavement condition responsive, where work is triggered when condition reaches a critical threshold in types of treatment options. The final treatment options for each of the road section regard to pi values are listed in the table for further analysis. Cost is particularly important in the stage of prioritization. It has to ensure that an adequate return in terms of benefits from committing expenditure. Any commitment of expenditure can consider as making an investment. The additional purpose is to ensure that the investment option adopted gives the highest return in relation to the time of the investment, the internal rate of return, IRR. With assigned color codes to reflect pavement defects severity, priorities are given to various road sections. Red represent the greatest severity, and green represent the least. This allows better clarity when making decisions of whenever part of the road network require early, substantial maintenance immediately after the treatment options are determined. A results analysis is performed to assign maintenance priority to pavement, which suffer the most deterioration, based on the priority index calculated. There are 3 types of maintenances. Preventive and corrective are maintenance to perform after a deficiency occurs in the pavement, such as loss of friction, moderate to severe rutting, or extensive cracking, may also be referred to as reactive maintenance. Emergency maintenance performed during an emergency situation, such as a blowout or severe pothole that needs repair immediately. This also describes temporary treatments designed to hold the surface together until more permanent repairs can be performed. To consider a treatment is cost effectiveness. 3 questions need to be answered. Does the treatment enhance pavement performance? Or would it last long enough even the pavement have been upgraded? Is the treatment cost beneficial? Does it give good returns in terms of increased life per unit of cost? What is the best treatment method to use? Is it the lowest average annual cost and the most effective solutions? These 4 selections factors represent the most important criteria when considering cost-effectiveness treatments, which are crack conditions, traffic loading, cost of treatments and pavement expected life. As the method of prioritization in first-generation decision support system is based on the function of present cost condition, further development of table representation of severity in pavement conditions is necessary. Similar to the table as before, red represent the most expensive treatment options, while green represent the least. Since there is lack of information supplied from client, the budget of overall project unknown. Thus, it is unavailable for cost to have a set of priority as the pavement condition data at this stage is not reliable. They do not realistically reflect the road condition. It is difficult to assign treatments options for each subsection. Instead, an indication estimate of cost is provided for reference. Nevertheless, the priority of maintenance of the pavements should always put pavement condition as the priority, as it can affect the safety of road user immediately. Decision-making flow is crucial for assigning treatments. It requires experienced engineers' judgments to set thresholds for which limits of defects cannot be exceeded. This decision flow chart provides an estimation of how treatments can assigned in the maintenance priority and cost table, which is based on percentage of defects calculated. To summarize, 2 subsections require substantial reconstruction. They are the first section of West Terrace Road and SW Campus, and the second section of Ring Road North. The first section of West Terrace Road and SW Campus suffered 28.49% of cracking, and 59.17% of polished aggregate on road surface, in the entire subsection road surface area. The second section of Ring Road North suffer in excessive cracking with 51.97% in its subsection's surface area.
Both of them have values greater than 3 in priority index. With regard to intervention level in Table 4, they require substantial reconstruction or further development, upgrade to ensure its safety features. The second section Ring Road South, RRSO2, and East Terrace Road, ETRO1, require an immediate maintenance. RRSO2 suffer a significantly number of cracks with 33.87% of crack, found in the overall subsection road surface area. The whole section of ETRO1 suffer with 71.45% of polished aggregate on road surface. Both of them have values in between 2 to 2.99 in priority index, with regard to intervention level in Table 4, which lead to immediate treatments options, such as cracks sealing, patching and overlay. 4 other subsections require routine maintenances, as the threat to road users are not immediately and can be scheduled with treatment in a later time. They are the first and third section of Ring Road South, and the third section of Ring Road North. 4 subsections does not require any treatment as their condition are regarded to be safe, as only small number of surface defects were found. They are the second section of West Terrace Road and SW Campus, both subsections in SW Campus and University Road West, and the fourth section of Ring Road North. Further improvement can be made in the data collection sections if advanced measurement equipment were used. For example, deflection of the pavement can be back calculated using FWD method. If falling weight deflectometer test could perform, the FWD model explore greater insight in the pavement response and performance in structural integrity of the pavement. The pavement performance model can be used to investigate the level of surface distress and structural performance of a pavement. These data are more reliable for a decision support system. However, it can be argued that using such advanced equipment will lead to greater burden in the cost of the project. Since most of the techniques of measuring defects are based on visual inspections, problems of repeatability and reproducibility are likely to be considerably greater. This is because inspectors may have various perception of the severity of the problems, particularly if they are from different regions. Using measurements condition rather than rating gives more accuracy in making decisions.